So continuing here with the urinalysis lab and the specific gravity. So that's an important measure because it tells you how many dissolved particles are there in a urine sample. And it really gives an indication of your hydration status. If you drink a lot of water, then your urine sample should be pretty close to water. So water has a specific gravity of 1.000. And if your urine sample is close to that, that means there's mostly water in your urine. Now, if you don't have that much water to spare and your kidneys have to put a lot of your metabolites and waste products into the urine sample, then of course you will have a much higher gravity because there's more dissolved stuff in the urine, and your specific gravity will be higher than 1.000. It would be on the high end would be 1.025. That's pretty high. Okay, and as I mentioned earlier, the urinometer, we have them in the lab, but I don't really like to use them because it's such a mess, spilling around with the urine samples. And anyway, and the cleanup is a mess too. The refractometers also, they don't give you any additional information. It's just a different way to measure the same thing, the specific gravity. Okay, so now the urine sediment, I'm going to refer you to that tutorial that you are supposed to watch for this week. It's a really good tutorial about somebody doing a urinalysis lab, and you're just watching them do it and explain about the different fields that are on a urinalysis stick. And it's a really good tutorial, so you should definitely watch it. And it also explains about urine sediments and what that would look like, so you should do that. Now, the unknown urine samples, unfortunately you can't do that, but if you get a chance, go to the 99-cent store and get like a THC test or a pregnancy test or an ovulation prediction kit, one of those. These urine tests, it's kind of interesting. Just do it for fun. It only costs like $1, and you can see you have to collect some urine and then put a few drops on a test strip or dip the test strip into the urine sample and then analyze it for different metabolites. I always in the lab I always ask to have enough test strips for the pregnancy test and for the THC test and for the LH test, which tests for the presence of luteinizing hormone, which is really high right before ovulation. So anyway, I'm going to explain it at the end, but here are your unknown samples. Unfortunately, you don't have to do these. You cannot do this, but it tests for the same items that we had before in your own urine sample. It's just that you're testing an unknown and then analyzing what the deal is with that urine sample. So it will be testing exactly the same things that you have right here, from leukocyte to glucose. Here, and from leukocyte to glucose, we're going the same thing. These are the same 10 fields that you're testing for. And then, of course, if you're finding, let's say, protein in your urine sample, then you would draw the conclusion that somehow there's probably inflammation going on. The proteins will get filtered out at the level of the glomerulus. If you find glucose in the urine sample, you would conclude that most likely this person has diabetes and so forth. Okay. So what I just was talking about answers basically question number 1. Again, so if you, for example, find glucose in your urine sample, then you would conclude that this person probably has diabetes. So here are some questions regarding your own urine sample. Obviously, you can't do that, but we're just going to go through it theoretically. So was sugar detected in your individual urine sample? Most likely no, unless you have diabetes and you maybe didn't even know about it. So you should not detect sugar in your urine sample. Protein is also a substance that you should not detect in your urine sample. And to state the significance of having albumin in the urine, that means that the glomerular filtration membrane is way too leaky and it's letting out the albumin. The problem with that is that you need the albumin for your colloid osmotic pressure to recapture fluids at the end of a capillary bed. So if you're losing that colloid osmotic pressure, then you don't have enough driving force, osmotic driving force to pull water back into your cardiovascular system. That means you most likely will end up with edema. And that's what you see when you have a patient that has edema. The first place I would look is the kidneys. I mean, of course, in places where people are starving and the body has started to digest your proteins, the albumin, for energy, then that's a different story. Then you might suspect that this person has been starving for way too long, and that's why they have the edema, the hunger bellies. But in the United States, my first guess would be that the kidneys don't work properly, and so I would look for that. And also, if somebody has edema, another place to look for would be the liver, because the liver makes the albumin. Anyway, so let's take a look at this excretion study table. And you're supposed to decide here whether it's normal to find the various components at the various places. And so let's go through some of these here together. Plasma proteins, of course, in the afferent arteriole, of course, yes. In the filtrate, it should not be filtered out, so no. In the efferent arteriole, yes, they should be there. Reabsorption, well, you didn't filter it out, so you can't reabsorb it. In the urine, also no. Absent from urine, yes, it should be absent from urine. In the venous blood, it should be yes. Red blood cells and white blood cells, that will be should be the same, being handled the same way. So red blood cells and white blood cells, they're both in the afferent arteriole. They should not be filtered out. They should stay in the efferent arteriole. They don't need to be reabsorbed. They shouldn't be in the urine, and they should be absent from urine. Yes, they should be in the venous blood, obviously. Glucose and amino acids are also handled together, so that we can lump these two together, just like these here together. So glucose and amino acids, they are in the afferent arteriole. So they're coming into the glomerulus. They will be filtered out both. In the efferent arteriole, you might find it, well, not really. They're pretty much completely filtered out. So we should not have any of these in the efferent arteriole, but we do need to reabsorb them. Those are nutrients that we want to keep, so put a check here. And you should not find them in the urine. They should be completely reabsorbed and absent from urine, yes. And venous blood, yes, you should find them in the venous blood. Next, let's take a look at sodium chloride, urea, and uric acid together, because they are handled the same way. So for the sodium chloride, urea, and uric acid, they're all highly water soluble. They are present in the afferent arteriole. So checks here. In the filtrate, they will be filtered out. They're small, very soluble molecules that will be definitely filtered out. They shouldn't be in the efferent arteriole, should be completely filtered out. To some extent, they are being reabsorbed because they're useful for osmotic pull. For example, at the loop of Henle, you need to have a certain amount of urea and sodium chloride. And then you should also find them in the urine, because some of it will be just excreted, whatever's in excess. Definitely uric acid is truly a waste product. Urea is also waste, and then too much sodium chloride, you get rid of it through the urine. So absent from the urine, no. And then in the venous blood, you will have some definitely left. Now the water should be pretty much everywhere, so we have definitely in the afferent arteriole and the filtrate. There's still some left, of course, in the efferent arteriole. We can't just run the blood dry there. You reabsorb most of it. Some of it will be in the urine, absent from urine now, but in the venous blood, yes. And then the last one is penicillin, and this is a substance that is foreign to your body, so you will have no reabsorption mechanisms for penicillin. So as this antibiotic penicillin is excreted via the kidneys, it will enter the glomerulus via the afferent arteriole, so you have it in there. It will be filtered out to some extent, not all of it, but some of it. Some of it will stay in the efferent arteriole. It will leave the kidney, the glomerulus again. You have no reabsorption mechanism for it, so this is blank. And then it will be present in the urine, and depending on how quickly your kidneys are excreting a substance like penicillin, that's how determines how quickly you need to take the next tablet, the next dose of it. So not absent from urine, and it will be present in the venous blood. So that's our excretion study table, and explain how regulation of urine output is related to osmotic balance. You need water to stay in osmotic balance, and so your kidneys will do a good job in excreting only the amount of water that you can afford to lose to stay in that osmotic balance. What causes the formation of urine crystals? That is when your urine is too concentrated. Sometimes substances will precipitate out and they will form urine crystals, and that can lead ultimately then to kidney stones, which is very painful. So it's a good idea to drink a sufficient amount of water, because you don't want urine, to form urine that's so concentrated that stuff starts precipitating out and starts to form crystals, or even in the kidneys it would form kidney stones. What's the significance of the urine sediments you observed under the microscope? I am going to refer you to that tutorial that you're supposed to watch. Most of the time we only see epithelial cells, and they kind of look like this. They have a nucleus right there, and then you will see probably some bacteria on there, the little specks. So here's the nucleus, and then you have little specks from the normal microbiota that's part of your these cells that you will find in a urine sediment. List the hormones involved in the regulation of sodium and or blood volume and explain how they work. Well, there are 3 that you should know, and that would be ADH, antidiuretic hormone. ADH inserts water channels into the collecting duct of the kidneys, and please listen to the lecture on the renal physiology. It explains it there really well, and also your water balance. So ADH will insert water channels into the collecting duct cells and reabsorb water directly. The aldosterone, that one reabsorbs salt. So that is a steroid hormone from the renal cortex, and it will insert salt reabsorption mechanisms into the collecting duct cells mostly. And with the salt goes the water reabsorption. So these 2 are very, very powerful reabsorption mechanisms. ADH, water reabsorption, so H2O, reabsorb. Oops, I hope we can read this. And aldosterone, salt. Let's put in salt, reabsorb. And again, please listen to the lecture on the renal physiology. And then we have the little midget, the atrial natriuretic peptide, the ANP. That's the 3rd one. And that one works directly antagonistic to aldosterone. That means we're excreting more salt. With the salt goes the water, so it's a natural diuretic. So it's directly antagonistic to aldosterone, and it's supposed to reduce volume in your body, and it's secreted from the atria of the heart in response to overstretching, too much volume. So it's a diuretic basically. Explain the physiological mechanism that results in increased urine output following ingestion of an alcoholic beverage. And that's an easy one to answer because alcohol will block ADH. So alcohol inhibits ADH. So if you inhibit ADH, antidiuretic hormone, then, well, you've not antidiuresis, but you have diuresis, and you have a diuretic. So therefore, if you are drinking alcohol, it will inhibit ADH, and you're going to have increased urine output. And that can lead to a hangover, a dehydration, headache, and hangover. So what you should always do is make sure when you drink alcohol that you drink sufficient amount of water with it to save yourself the headache. Question 11, why does insulin deficiency result in hyperglycemia? Well, because insulin is needed in order for cells to pick up glucose from the blood. And so if you don't have insulin, then these cells cannot pick up take in the glucose for energy metabolism. And so the glucose stays in the blood, and that gives you the hyperglycemia. In terms of filtration reabsorption rate, why does hyperglycemia result in the presence of glucose in the urine? Well, glucose is a small molecule, and it will be always filtered at the level of the glomerulus. So that means that you filter it all out. Now you need to reabsorb all of it. But if it's so much that your reabsorption mechanisms are maxed out, then you end up having some of it. It will show up glucose in the urine because you weren't able to reabsorb all of it, all of the stuff that was filtered. It was just way too much in the blood already. And here, so at the end, these are some additional urinalysis tests that I like to do with students. They're easy to do. We have these test strips in a lab, and they're very common. You can just go to a store and buy these. The pregnancy test is looking for the hormone human chorionic gonadotropin that's only present in pregnancy, and that's the basis of the pregnancy test. The ovulation prediction test looks for the spike in the hormone LH, the luteinizing hormone, and the THC test looks for the metabolites of marijuana. You should know this because I might put this on your quiz. And So that's it for this lab, but make sure that you study this. Take a look at the tutorial, please.